This is 9.6 ratios in the root test. So far we have learned quite a few tests to determine whether series converges or not. I'm going to review a quick one first, as this might be related to the test that we're discussing in this section. Do you remember the geometric series? Okay, so the geometric series. Okay, so again, what's geometric series? The geometric series should have the form a and then r to some power n, no, n minus 1 actually. It doesn't matter. But what does matter is when you have a series that you have a common ratio raised to n minus 1 power. And particularly when you write out explicitly, what you should see is the ratios of two consecutive terms is the same. Okay, so like in this case, if this is your first term, second term, and third term, and if you're looking at a 2 over a 1 or a 3 over a 2 or 8, 4 over a 3, by forming all the consecutive terms, okay, they are equal, the same. Okay, so it's always the same, and it's equal to the common ratio r. And this is why the term common ratio comes in. Right? So, for example, when you have this series, 3 to the n power n from 1 to infinity. So you see if the first term is 3, second term squared is 9, the third term is 27, then that's 81, and so on. Now, if you form the ratio 9 over 3, 27 over 9, 81 over 27, you always have the same, that is 3. Okay? So, now this is a very special test of a special series we call geometric series. It's the ratio of consecutive terms always the same. However, most series, of course, the ratio is not the same. We're gonna extend this idea basically to a whole bunch of series where the ratios of all of these are not the same, okay, but they are close, okay. So let's say you form the ratio, the second and first term is not 3, is 2.7, and then ratio of the next two consecutive terms is 2.8, the next two will be 2.9, and as you're going to form the ratio looking at these ratio as n goes to infinity, you see it's approaching to a constant, okay, a constant. Then we can use that to conclude, very similar to geometric series. Recall in geometric series, when does the series converge? The series converge when converges when the absolute of r less than 1, right? And then diverges otherwise. So now we have the similar test where that so-called common ratio is not common ratio, but it's the ratio of two consecutive terms approach a constant. And if the absolute values of that constant is smaller than 1, the series would converge. So here is the statement of the ratio test. For a series like this, right? Suppose if we look at the limit. You see a sub n plus 1 over a sub n, right? So that's the ratio of two consecutive terms there, n approach infinity. Notice that I put the absolute value bars there. Instead of at the end, you put the absolute value, but it's basically you put the absolute values at the ratios here, okay, instead of at the end. So let's say the limit is L. Then you see that if the L smaller than 1, then the series converges. And because I put the absolute values in, basically testing the series with the absolute values of the terms, so if it converges, then it converges absolutely. And similar to the geometric series test, the limit L here is bigger than 1, we know that the series would diverges. Here's a little bit difference, is when the limit is precisely 1, then this test is inconclusive. Now, it's the reason why it's conclusive is because if the ratio is about 1, right? Again, taking the limits approaching 1. I don't know it's approaching 1 from the left or from the right. In other words, if the ratio is approaching 1 but slightly smaller than 1, then that means that series will be smaller. Well, when the term is going to be smaller, right? If the ratio is smaller than, so less than 1, then the next term is going to be smaller than the previous term, so your term is shrinking. In that case, would converge. But if the term is increasing, will be divergence. So when the limit is 1, so I don't know which size approach, so I cannot tell whether the series converge or diverge. Okay. Now look at this. The test here relies on the ratio of two consecutive terms, and you're taking the limit and approach infinity. So this test worked really well for a series that involve factorials and constant raised to the nth power. Now the reason is because when you factorials with n powers, there are a lot of cancellation going on. It makes the limits easy to find. Okay, so let's look at the first example here. Test this series 1 over 2 to the n times n factorial. You see that there's a factorial, there's an n powers, and this makes the test very easy to use. Okay, so let me do number 1 here. Let's say, all right, so that's that. What's a sub n? Again, a sub n is the general terms here. According to the ratio test, we need to take the limit of the a sub n plus 1 over the a sub n, they're both in absolute values. Okay, and in this particular case, the a sub n, what's a sub n? A sub n is this, right? So let me write the bottom first, maybe it's easier. Right, the bottom is a sub n, which is 1 over 2 to the n times n factorial. The denominators is a sub n plus 1. So you're replacing the n with n plus 1, and we have 1 over 2 to the n plus 1 times n plus 1 factorial. Okay. Now, if you have this fraction divided by fractions, means you multiply by the reciprocal, and that means we would have that time the reciprocal, so 2 to the n time n factorials on the numerators now over 2 to the n plus 1 times n plus 1 factorial. All right. Now, all it's boiled down is to try to figure out what this limit is. Now, as you looking at the common factor, you see 2 to the n and 2 to the n plus 1. So this really 2 times 2 times 2 n times. This is 2 times 2 times 2 times 2 n plus 1 times. So they all have the 2's in common. You cancel everything except there is a 2 left on the bottom, right? It has one more 2 than the numerator does. Now, if you look at the n factorial and n plus 1 factorials, don't forget that n factorial means what? 1 times 2 times 3 times 4 up to n. And this one means 1 plus 2 times 3 times 4 times 5 up to n plus 1. So all the factors in n factorials and n plus 1 factorials are the same, except the largest term here is n plus 1 survive. So that means this and this cancel. You're left with n plus 1 at the bottom. And so this series would become, this limit would become limit of what's left? Nothing, right? So it's only 1 on the numerators, 2 times n plus 1 on the denominator. Now from here it's clear, as n goes to infinity, this approaches 0. Therefore, that equals 0, less than 1. According to the test, it says the series converges. Okay, converges. In fact, we know it converges absolutely, but it doesn't ask, so it just say the series converges and by the ratio test. Right? So again, you see that the problem relies on really the finding the limits. It's again, finding limits is easy as long as we know how to simplify the factors, common factor with the n factorials and the n powers. Before we get to number 2, let's do a kind of quick review on the simplifying factorials here. So let's say you have n plus 2 factorial over n plus 4 factorial. Okay, so again, what you're going to do is looking at these two numbers, n plus 2 versus n plus 4. So the n plus 4 is 2 units above the n plus 2. So essentially what you have is 1 times 2 times 3, and then up to n plus 2. And then the denominator you have 1 and 2 times 3, and then up to n plus 4. Right, up to n plus 4. But where's n plus 4? Well, before you hit n plus 4, you gotta hit n plus 2, right? And then the next one, n plus 3, and then the n plus 4. So you see that all of them really cancel except these two. So it will be 1 over n plus 3 times n plus 4. Okay. Here's another example. Let's say you're going to have to find 2n factorial over 2n plus 2 factorial. Okay. Once again, this one is 1 times 2 times 3 up to 2n. The denominators is 1 times 2 times 3 up to 2n plus 2. But what's before 2n plus 2 is 2n plus 1. And what before 2n plus 1 is 2n. So you see again, all of them cancel, and we left with 1 over 2n plus 1 times 2n plus 2. Okay, now that's really helpful when it comes to simplifying factorials, like in example 2 down here. For the example 2, again, you're going to looking at the limits of the absolute of a sub n plus 1 over the absolute of a sub n and approach infinity. And in this particular case, we got the limits and approach infinity. What is a sub n plus 1 and what's a sub n? Now, when you have a sub n plus 1 divided by a sub n, you will have a, I'm going to skip step there. When you divide, it means multiply by reciprocal, right? So what's a sub n plus 1? Replace the n with n plus 1. So you're going to have n plus 1 plus 1, so that's n plus 2 factorial over n plus 1 plus 1, so that's n plus 2, and to the n plus 1. So this is the a sub n plus 1. Actually, I should have absolute values there. I should have absolute values there as well. But because these are positive terms, so absolute, that doesn't change. Okay, so I'm supposed to divide by a sub n, but skipping that step, when you divide by a sub n, which is a fractions here, it multiplied by the reciprocal. So I multiply by n plus 1 to the n powers over n plus 1 factorial absolute values. Again, I could drop all the absolute values because it doesn't matter. It's all positive terms. Now, let's look for the simplifications or canceling common factors. Can you spot that? Looking at a factorial first. See n plus 2 factorial, n plus 1 factorial. These two could cancel. So this is 1 unit above the n plus 1. So the n plus 2 is the only factor survive. The rest, 1 through n plus 1 and 1 through n plus 1, they all cancel out. And then so I'm left with n plus 1 to the n and n plus 2 to the n plus 1 there. Okay, so let me rewrite this. I have the limit here and approach infinity, and that is n plus 2 to the n plus 1. And let's put it on top, so that's n plus 1 to the n power. Okay. Now, this is the one, actually, I could simplify first. It's n plus 2 and n plus 2. I could simplify a bit more, right? So that one cancel with one of those. So it's just n plus 2 to the n power. And the numerator and denominator actually has n powers, by the way. Or thinking of this as the limit of, if I combine, it's really the n plus 1 over the n plus 2 raised to the n power and approach infinity. Okay, now we see that what's really approaching 1 there to the n, so that really approach 1. So the limit is 1. Now, when the limit is 1, this test is inconclusive, meaning I don't know the answers. So inconclusive. Okay, so inconclusive. So that means this ratio test failed. So I'm going to stop here actually. So I cannot do number 2 with the ratio test. You have to use a different test. All right. And finally, the example 3. You see, this one is an alternating series. It's an alternating series. Now, it's alternating series. However, the alternating series test cannot be used, or it's very hard to use as you're trying to test these terms over here, whether limit approach 0 or whether it's decreasing. So I'm going to use the ratio test in this case. Again, taking the limit of absolute of a sub n plus 1 over the absolute of a sub n. And in this case, the absolute values actually doesn't matter as we have negative terms in it. Okay, so we have the absolute values of, again, what's a sub n plus 1? You replace all the n with n plus 1, which give us n plus 2 here, time n plus 1 factorial over, and I have n plus 1 to the 7 and 3 to the n plus 1 after the values. Time. We're going to do time instead of divide by a sub n. We do time the reciprocal of this, turning the denominator into the numerator, so that is n to the 7, 3 to the n. The denominator would be negative 1 to the n plus 1 in time n factorial. Okay. Now here, if you look at the factors, here is absolute of the negative 1, right? So these are negative 1 terms. So it doesn't matter negative 1 and positive 1 is raised in the power. You take the absolute values, this turn into a 1. Okay. Same thing, these absolute negative 1 will turn into 1. Okay. And we also know the factorial could be simplified. You see the n plus 1 factorial and n factorial here. Okay, so these will also cancel, and that's left with n plus 1. Okay, and what else I have? Say, 3 to the n plus 1 and 3 to the n. 3 to n plus 1 and 3 to the n, we could also cancel. What's left? There's 3 left on the bottom here. Okay, so after all, we have the limit of n approach infinity. I actually don't need the absolute value anymore. Now it's turn into positive, not into 1. And then I have the n plus 1 left over here times, that's over n plus 1 to the 7 power times 3. And on this side, I have n to the 7 over, nothing left, it's a 1, right? So it's just the 1's left there. Okay, so what is this limit now? Well, if we look at this carefully, it's n plus 1 to the time n to the 7, so that will give us a let's multiply that out. So n to the 8 power plus n to the 7 power over, and then you have 3 n plus 1 to the 7 power. So we actually end up with the polynomial over polynomial, and that's 8 power, that's 7 power. So the limit here will be infinity. So it's clearly bigger than 1, right? It's getting huge, and therefore we conclude the series diverges right, by the ratio test.